wabarakatuh. Today's topic in this video, I will explain about minor losses. And previous video, I've already explained about the Hagen-Porcella derivation, and then I've already mentioned about the major losses. Now I will explain about minor losses. Okay. As we know, in a piping system, we have two different types of losses in terms of the frictional losses, which are first major losses and then the minor losses. And major losses, we already know that it will use Darcy-Weisbach equation. And then for the minor losses, I will explain in this video. So in this video, in this slide, the objective is to acquire fundamental concept of laminar flow in circular pipe. Actually, this is not not necessarily laminar flow, because we have three types of flow, which is laminar, transition, and turbulent flow. In this chapter, the learning outcomes is one, at the end of this chapter, students should be able, one is calculate pumping power to overcome pressure losses in pipe. So basically, in this chapter, I will not explain more on the pumping power calculation, because it has a specific topics. Okay, after this, chapter 9 will be focusing more on the pumping power and pump lah. Okay, and second is calculate head loss due to sudden enlargement and sudden contraction, and then calculate losses in pipe due to fittings, bends, and pipe entry. All of these losses is actually minor losses in the pipe. So if there is a sudden enlargement where we have different areas of pipe, for example, pipe from 100 millimeter flows into 50 millimeter to 150 millimeter of pipe diameter. So that is sudden enlargement, okay, from smaller pipe to large pipe. Okay, for the sudden contraction, from a larger pipe to the smaller pipe. And then when we have a piping networks, so what we have, for example, we want to transfer water. Okay, if I can draw that figure. Okay, let's say we want to transfer water from a reservoir. Let's say this is reservoir, and then we want to transfer that water to our tank. Okay, we want to transfer from point A to point B. So it is not necessarily we will use straight pipes up to the point B, because we have to measure the major losses and minor losses. For your information, major losses contributes a lot of friction losses in a pipe compared to minor losses. So if we want to transfer from point A to point B, we cannot use straight pipe from point A to point B. For example, these straight pipes maybe takes 20 meters to transfer from A to B. So what happened? The friction losses, major friction losses, will contribute a lot to this pressure drop. So what will happen if you have higher pressure drop? You will require pumping power, more pumping power, which you are required a larger pump. So more pumping power, its significance, it will brings, or it will actually need bigger size of pump, okay, to give this delta P amount, okay, pressure loss amount to this system, in order for the system to transfer A to B. So pump will supply energy based on the delta P required. Okay, the delta P required is actually the delta P that loss from the major losses from the piping network. So we cannot remove the delta P. We cannot totally remove it unless you are using a gravitational acceleration. For example, as you can see, there is a tank in Taman, for example, which located at some elevation from the ground, and then this is perumahan. So we have these kinds of arrangement. Why? They only need water to be pumped to this tank, and then after that the distribution from the pump to the taman will be used gravitational works. Okay, it will use gravitational to help distribute water to perumahan. So that is what that way you do not need pump, because that delta P we do not have significant loss of delta P. Okay, that's why we as we can see, there is a lot of there is different elevations of this tank from one house, from one taman to one taman. Okay, so this is the arrangement for the gravitational. The distribution the distribution networks and the water will distribute this distribution networks by using a gravitational works. So if you want to transfer water or fluid from point A to point B with some elevation here, so what you have to do is you need to calculate how much pressure losses in this system. So if you calculate that the pressure losses, and then you will supply this data to the pump supplier, or to the pump supplier, then they will suggest to you to use what kinds of pump. Okay, how big that pump is, and it depends on your delta P. So delta P required to flow your water from A to B. That's why we are calculating delta P, or sometimes we are referring to delta P with HF or H. This is total heat. Okay, total heat. So in order for you to flow water A to B, you need to know what is total heat. So if you supply pump with less than delta P, okay, the pipes the water will not flow, okay, because it does not have sufficient energy to flow A to B. Okay, and then the last one, determine the equivalent length LE. So your level, you will not use equivalent length, okay, to determine what is losses in the pipe. So as we know that HF is H minor plus H major. Okay, if you are using the equivalent length, you will only use Darcy-Weisbach equation, where H minor, okay, will be changed into equivalent length. Okay, that equivalent length will be substituted into this. So in terms of L, okay, it will substitute into Darcy-Weisbach equation. Then you will calculate what is the what is the losses in the pipe. Okay, so this is the energy relation in order for you to calculate what is the pressure loss. Okay, or no, sorry, what is the pumping power. As you can see here, W dot is a pumping power. So please remember this equation in order for you to calculate what is pumping power. So pumping power will be using Q times with delta PL. So this delta PL is a total loss, a total pressure loss. Okay, loss. And then Q is volumetric flow rate. So rho is density, G is gravitational acceleration, and HF here represent the total heat loss. So which means you have to calculate the total heat loss before you can supply or you can plug in into this equation. Total heat loss will be solved, okay, by using Bernoulli's equation, and after this I will show you in the example and the exercise how to calculate the total heat loss. Okay, so please remember this equation in order for you to calculate what is the pumping power. So this is pumping power, W dot pump L equal to Q rho GHF. Either these three, whichever yang you want to use lah, okay, either this one or this one or this one, M dot GHF. So that is pumping power, okay. And then after that we go through to the minor losses. The heat loss is long straight section of pipe can be calculated by using a friction factor obtained from Moody's chart. So this is what I've told you before. We will use the Darcy-Weisbach equation. Okay, Darcy-Weisbach equation. So where in the Darcy-Weisbach equation we have a friction factor here. So that friction factor will be evaluated by using a Moody's chart. So Moody's chart I've already teach you on how to refer to the Moody's chart. I really hope that you gone through to that video and then you already understand what I've talked about. Okay, so most pipe system however consists of considerably more than straight pipes, like I said before in this figure. So I draw it again. So if you want to transfer from point A to point B, from the reservoir here and then to the point B, where the point B is at the surface of water in a tank. So you have a tank here. So you are not using a straight pipe from A to B, since straight pipes will contribute major losses, contributes a lot of pressure losses. Okay, and then in order for us to reduce the pressure losses, we might use a piping system, but again do not overuse piping system, or do not overuse the fittings, because a lot of fittings will contribute a lot of losses in the pipe. So less is more. Okay, so for example, if you want to transfer from A to B, maybe you have to suck the water here, okay, flow the water up, and then you will use 90-degree elbow here. So better I change to the color of the red color. Okay, let's say you want to transfer A and straight up, and then you will use one fitting here, 90-degree elbow, and then you will transfer straight, and then you will use another 90-degree elbow here, okay, and then you will transfer up to this point B. Okay, you are only using two fittings. And for the major losses here, maybe it will require less maybe it requires much more less in pipe length compared to from A to B, straight from A to B. So this will from A to B will bring straight pipes will brings you a lot of major losses, which is contributes to the delta P. And then if you are using this, maybe you will for example, that point A to point B, you are using 20-meter pipe, straight pipe. So by using these fittings, you might need less than 20 meter, maybe 15 meter. So you are reducing a lot of delta P actually. Maybe you see that 20 and 15 is not much. is about 5 meter, but in terms of delta P, it will contribute a lot. Okay, for the major losses, it will actually major losses contributes a lot to the delta P compared to the minor losses. Minor losses may be around for the 50 meter. For example, if major losses contributes 20 meter head loss, major losses, for the minor losses, I put it M, uppercase M, major. So for the minor losses, maybe it will only contribute 0.5 meter. So much more less compared to the major losses. So in order for you to design a piping network, please avoid straight pipe from A to B, long pipe, okay, with a length of more than, avoid a long pipe, okay. Maybe you could reduce, if you cannot avoid that, you want to transfer from A to B, the length of that point is 20 meter, for example, like this. So if you want to transfer from point A to point B, so you have to transfer for about 20 meter here. So you cannot avoid these kinds of straight pipe. Maybe you will use this 20 meter, but you will reduce some other points lah, okay. So do not use a straight pipe. Do not use long straight pipe, okay, because major losses contributes a lot to your delta P. Okay, these fittings, additional components. For the fittings, we have some list for the fittings here. As you can see here, we have gate valve, globe valve, spherical plug valve, and many more. So each of these have different K value. So I will talk about the K value after this. How can we use the K value in the question, in the equation? So such losses are generally termed minor losses, and sometimes they are ignored when the friction losses predominant, which means that if we have a major and minor losses, sometimes the minor losses will be ignored, generally can be ignored, because it does not contribute a lot to the delta P. So what compared between major and minor losses does contribute a significant effect to the delta P, okay. So in many cases this is true. In other cases, the minor losses are greater than the major losses. Not necessarily all the minor losses will be neglected or will be ignored, since it has a small value. But sometimes in some cases like this, the minor losses will contribute a lot. It depends on the cases, and most of the time minor losses contribute less effect lah, okay, less effect to the delta P, okay. In this section, we indicate how to determine the various minor losses that commonly occur in a pipe system. So what equation that will be used in order for you to determine the minor losses is this. Please remember this equation, okay. So where the K is a loss coefficient depends on the types of fitting that is present. As I mentioned before here, this is K value. So we have K value, and then we will substitute into this equation, okay. So as you can see here, gate valve open to 75%. Normally we will use 25 compared to 0.25. Okay, we will take the greater value of K for a gate valve, because gate valve in this table gives us in the range of 0.25 to 25. So basically, when you are when you get the final exam question, all the K's value will be given to you. So here we have V2. V2 is a velocity, and you have to square the velocity divide by 2g. G is a gravitational acceleration. That is the equation will be used in order for you to determine minor losses. Sorry. Okay. Now this is types of minor losses, we have a sudden contraction, and this is enter loss entrance loss, okay. And then we have sharp edge, and all of these you will be using one equation, h equal to kv squared over 2g. So you do not have to worry, and the k values will be given in your question, okay. So now we take a look at the question here, the exercise. This exercise, in order for you to determine what is how to calculate how to answering the question for the question in this chapter, because this exercise concludes everything, which means from the major losses and minor losses, how you will find and how you will use that major losses and minor losses equation in one question. Okay, the figure below, so we have the figure here, shows the plan view of a group of horizontal pipes made of galvanized steel connected in series. So from the first statement, we know that this is a plan view. So when we have a plan view, which means that this pipe is in a horizontal, so on the ground, for example, so it does not have any elevation. So that means the total head loss between ends A and B, if the pipes are 100 millimeter diameter, conveying water at a rate of 15 liter per second. So all the information about the density and dynamic viscosity is already been given. Then given also the absolute roughness. So as I mentioned before, if in the question or gives you the roughness, so you do not know whether that is when you want to refer to the Moody's chart, you have to remember that in the Moody's chart, the values represent for relative roughness, which have no value for the relative roughness, okay. So which no value, not which have no unit, okay. So this is absolute roughness, therefore you have to find what is the relative roughness. So how many fittings, how long these pipes, so you have to refer to the figure. Sometimes it will give in the question, it will give you the amount or how many fittings used in the pipe in the piping networks. Sometimes they will not give you any info in the question, but it will give you the info in the figure. So as in this question, we know that all the information about the fittings, how much fittings and what types of fittings that will be used is given in your figure. So in this figure, we know that the piping networks will be used wide open globe valve first, and then we have 90-degree bend, and then another 90-degree bend. So we, in these piping networks, we will use two 90-degree bend and one wide open globe valve. So let's take a look on how to solve this problem. Okay. So so first we have to calculate in this question ask us about the total head loss. So for the total head loss is actually we have to find what is a delta P over rho G from Bernoulli's equation. Okay, so I will derive the Bernoulli's equation first. So we know that Bernoulli's equation is P1 over rho G plus U1 square over 2G plus Z1 equal to P2 over rho G plus U2 square over 2G plus Z2. So this is Bernoulli's equation in chapter 5, but now we are in chapter 8. So therefore we have another terms here, another parameters that will be included in the Bernoulli's equation, where we have HF. So this HF consists of H major, and then H minor. Okay, you have to calculate both of these value in order for you to calculate to get what is the HF. So now let's take a look at the question. Okay, I use P1 and P2 since we always use 1 and 2. So but in this figure we have A and B. Okay, so now what we have to take a look at is to cancel out some of the terms inside of this Bernoulli's equation. So as we know that if we have same diameter, so we know that in this question we do not have different size of pipes used for the piping networks. Therefore the velocity at 1 and 2 is the same. So if we bring this U2 to this side and U1 minus U2, both of them have the same value, therefore it can be cancelled out. So another terms that will be cancelled here is Z. Since this is a plan view, therefore we do not have any elevation for the piping networks from point A to point B, therefore we can cancel out Z1 and Z2. So because of the question asked us about the total heat loss, therefore we have to rearrange this equation into P1 minus P2. As I mentioned before, if we have P1 minus P2, this is pressure loss. Okay, pressure loss. If you rearrange the equation into P1 minus P2, this is pressure difference. Okay. In order for us, here is a pressure loss. If we change into the heat, this would be heat loss. Okay, heat loss. And this is, oh no, heat. Okay. Now we have the heat loss here. So if we rearrange this, P1 minus P2 is a total pressure loss. In other words, we can say it as total heat loss. So now we already cancel out some of the terms here. So rearrange the equation into P1 minus P2 because we want to find the heat loss. So P1 minus P2 over rho G. So equal to HF. So now if you bring the rho G here, this would be delta P. Okay, this would be delta P. If you bring rho G to this side, so it will change into delta P equal to rho G HF. If you remain like this, it will be heat, total heat loss. So H equal to HF. So total heat loss is equivalent to frictional losses. So as I mentioned before, this HF consists of major and minor. Therefore, H is H major plus H minor. So now our job is to find what is H major and what is H minor. So let's take a look at H major first. So I will calculate for the H major first. So H major, we know that it will use Darcy-Weisbach equation. Where Darcy-Weisbach equation, we will use HF because this is still in frictional losses. So HF is a friction factor L over D V squared over 2G. So now we have this equation, Darcy-Weisbach equation. What we have to do is we need to find what is the friction factor first. In order for you to determine friction factor, what you have to do is number one, you need to calculate Reynolds number. Okay, that is number one that you have to determine, because we have to determine either it is laminar or turbulent. Okay, and sometimes it might goes to the transitional state. Okay, so transitional is in between here. Normally we encounter laminar or turbulent flow problems. So number 2, after we found the Reynolds number, we calculate the Reynolds number. What we have to do, we need to find the relative roughness. So relative roughness, sometimes in the question they will give absolute roughness. So this absolute roughness will have units in it. So unit is maybe in mm or m or centimeter. Therefore, if you, in the question gives you the absolute roughness, you have to divide with diameter. So to find relative roughness, absolute roughness must be divided into with diameter. So both of these parameters needs to have the same unit. Since we need to cancel out, this is dimensionless. Relative roughness is dimensionless. And after you find these two values, then after that you will refer to Moody's chart. So for what? So you want to refer to Moody's chart in order for you to determine what is the friction factor. This is our main, this is our aim for looking at the Moody's chart. And then after you know what is the friction factor, therefore you will substitute into this equation. So L is a total length, D is a diameter, V is a velocity, G is a gravitational acceleration. Now we have to find what is Reynolds number. So the equation for Reynolds number is rho VD over mu. So now we have density, we have diameter, we have dynamic viscosity. What about the velocity? This question does not provide us with velocity value. So what we have to do from this question, we know that the rate already been given 15 liter per second. So now we have to find the velocity from 15 liter per second. So the Q, the discharge rate, has been given as 15 liter per minute. 15 liter per second. So we have to change this into meter cube per second since we are dealing with SI unit. So times, 1000 liter equivalent to 1 meter cubic. So here we will get 0.015 meter cube per second. That is our Q in SI unit. So what we have to do, from the Q we will find what is velocity. So Q equal to UA. So U is equivalent to Q over A. So Q is 0.015 meter cube per second divided by pi. Diameter is 100 divided by 4. So from here you will get your velocity is about 19.10 meter per second. Now we already find what is velocity. So what you have to do is to substitute into this equation. So Reynolds number equivalent to 999.7, you times with 19.10 times with 100 times 10 to the power of minus 3 divided by 1.14 times 10 to the power of minus 3. So after this, so please do this in line because I do not have enough space. That's why I bring it into this. I wrote it down into this kinds of arrangement. So if you have enough space of the paper, then you have to write it down in a straight line. Okay. So your Reynolds number here is 1.67 times 10 to the power of 5. So this one, as we know that whichever Reynolds value that below than 2400, this is laminar. And whichever value Reynolds number that is greater than 4000, it will be considered as turbulent. So now our value here is much more greater than 4000. Therefore, this is turbulent flow. So you can write it down here. So the turbulent flow. So what we have to do after we know that the Reynolds number, we have to find the absolute roughness, relative roughness. So since in the question does not give us the information about the relative roughness, but only gives us about the absolute roughness, therefore we have to find what is the relative roughness. The relative roughness is epsilon over d, where the epsilon is absolute roughness and then d is a diameter. So what we have to do, we have to substitute the value 0.15 mm and divided by diameter is 100 mm. So you will get your value is about 0.015. So we already know the relative roughness and what? And Reynolds number. So after that, the step 3 is to find friction factor from Moody's chart. So this is the friction factor, this Moody's chart. Okay, we know that our value of Reynolds number is 1.67. So I will round up into 1.7. So after I take that point and then I will bring it straight up to this straight upward, okay, and then I will try to find what is the relative roughness, the position, the location of relative roughness. Your relative roughness is 0.015 here. So this is our relative roughness. So our point, sorry, it should be 0.015. Sorry, I've made it wrong. So it should be 0.0015. Okay, your point is 0.0015, which is in between 0.02 and 0.001. I've already explained to you on how to check, how to find the intersection point. You have to find between these 2 points. Okay, take a ruler and do some interpolation here, and find the point of intersection from this point with this line. Okay, we want to find the point of intersection. So this is the point of intersection. After you get this point of intersection, you have to drag to friction factor F. So calculate and then do some interpolation here and find what is F. So F here I get 0.02275. So now we know that the F from Moody's chart is 0.02275. So this steps is under major losses. Okay, so now what we have to find is, we already know all the values in the Darcy-Weisbach equation. This Darcy-Weisbach equation is F L over D V squared over 2G. Now we already have F, L, D, V and G. So substitute all the values, all the information into this equation. So our F is 0.02275, and then you have to times with the L is 10, diameter is 100, times 10 to the power of minus 3, and times with 19.10 to the power of 2, divided by 2 times 9.81. So from here we will get HF is 42.33 ohm. So this is major losses. Okay, you already found your major losses. Now we move to the minor losses. Okay, so I will find what is the minor losses. So minor losses will be using HF equal to K V squared over 2G. So this is the equation. So this K is coefficient that will be given in your question. If not, it will provide you in the appendix the value of the K Okay, v is a velocity in your pipe, and then 2g is a gravitational acceleration. So let's take a look at the figure, because in the question does not give you in a statement how much fittings used and fittings used in your piping network. Therefore we have to find from this figure. So we have one. Oh, I'm sorry, because I do not explain to you about these major losses. Okay, these major losses, we have length here. This length is total length. So, sorry, I missed this information. So, L here is total length. Total length. So, how to find the total length? How to find the total length? So take a look at this figure. So we have 4 meter here. From here 4 meter, 4 plus 3, okay, and plus 3, okay, you will get 10 meter. It doesn't matter. For example, if you want to find transfer A to B, so you have 4 meter pipe length, and then up to point B is 2 meter. So even though this is not a plan size, plan view, this is elevation, okay, 2 meter. Z1 minus Z2 is 2 meter. Even if you already use this point Z1 and Z2 in your Bernoulli's equation, you still need to use this 2 meter in order for you to find the major losses in your pipe. So your total length in your pipe will be 4 plus 2. Okay, even though this is elevation, you have to calculate it, because pipe here still have relative roughness, and still have friction losses, still have the pressure losses due to the friction. So now here pressure losses will be due to the friction, and then due to elevation. Okay, you have to consider these two when you have some elevation, that the point from the point A to point B with 2 meters. So you have to calculate the friction, this 2 meter friction, where this friction is a major losses. You have to add the length of the pipe 4 meter plus 2 meter, and the elevation Z1 minus Z2 also will be 2 meter. So do not say that, do not pin in your mind that I've already used this 2 meter in elevation. It does not I'm not necessarily required to plug in this value into my major losses, since I've already considered it by using Bernoulli's equation, in the Bernoulli's equation, Z1 and Z2. No, so you still have to consider in both friction, major losses, and elevation. Okay, so now we move to the minor losses. We want to find what is the minor losses, how many meter, okay, for the minor losses. So now we have one open globe valve, this is one, and then for the 90-degree elbow we have one, and here we have two. So in these piping networks we will use two 90-degree bend and then one globe valve. So refer to this figure, this table. Globe valve is 10, the value of K is 10. Take out this value, K is 10, and then 90-degree elbow is 0.9. So let's calculate the minor losses for this question. Okay, so to find the minor losses, what we have to do, H minor equal to K globe, because we use one globe valve, so V squared over 2G, you have to plus, okay, K 90 degree, 1K 90 degree band, V squared over 2G, plus we have another K 90 degree band, and V squared over 2G. So we have 1, 2 90-degree bend and 1 globe valve. So K globe valve, as we see before in the table, K is 10 and K 90-degree bend is K globe is 10, K 90-degree is 0.9. So as you can see here, we are actually can combine this equation. So HF equal to K globe plus K 90-degree bend plus K 90-degree bend and then V squared over 2G. Okay, HF equal to K globe plus 2 times with K 90-degree bend. So V squared over 2G. Oh, okay. So, which means that you just need to add up K value only because velocity is the same for all the pipes. Okay, therefore we do not have to calculate one by one. Instead, we calculate one by one. We can actually sum up all the K's value and then we times with velocity squared over 2G. Okay, that is how to calculate the HF. Then we have to substitute all the values to find what is HF. So our HF is K globe valve is 10 plus 2 times with 0.9, okay, times with our velocity is 19.10 square over 2 times with 9.81. Okay, your HF is about 219.41 meter. So in this case, as we can see, H minor is much more greater than H major. So we cannot ignore the H minor here. So now lastly, okay, we know that from derivation of the Bernoulli equation, we know that delta P over rho G is equal to HF. So this is H, total heat loss, equal to H major plus H minor. Now what is your H major? From here, our H major is 42.30. Okay, your H major is 42.30 meter plus your H minor is 219.41 meter. So from here, your total heat loss is 261.70 meter. So you already answered the question. So that is how you find total heat loss. If the question asks the total heat loss, you have to follow that step. If I teach you in this video, so you have to use Bernoulli's equation, rearrange the Bernoulli's equation into P1 minus P2, and then find all the information. Basically, in this chapter, you have to find what is the major and what is the minor. So both of these value needs to be found first. So before I forget about to explain you about this Moody's chart. Okay, before this, I do not mention about the smooth pipe. Okay, if in the question does not give you any value or any values for the absolute roughness and relative roughness, so how can we find the friction factor? You will assume, okay, remember, you will assume that the pipe is smooth pipe. Okay, if after you assume that it is a smooth pipe, so take a look at here. So here, this is smooth pipe. So when you have your Reynolds number, bring it up straight, and then smooth pipe here, intercept, and then you drag to F. So if you have this Reynolds number, drag, when you attach to this, intercept, and then drag here. So this is the smooth pipe. Okay. If that case is if in the question does not give you any value for the absolute roughness or relative roughness, unless the question says that frictionless is negligible. Friction is negligible. Okay, neglect friction, neglect frictional losses, then we can neglect that friction. Okay, major or minor losses. And sometimes the question will told you or states that minor losses will be neglected, or the losses from the fittings will be neglected. So it means that minor losses will be neglected. So you no need for you to use equation for the minor losses to find K value, to find the H value, total for the head loss value. Okay, that's all for this subchapter, the last chapter, and the end of the chapter 8. And after that, after this, next week we will